talk about equations for circular motion. So the definition of period, I'm going to start with that. This is how long it takes to do something, time it takes to do one cycle. Okay. The unit for that is seconds or some kind of unit of time. Example of that would be like it takes the period for the Earth to go spin one time around is 24 hours. So the period of one rotation. It takes the Earth a year to go around the sun. That would be a period for one revolution. But typically, we're going to use seconds for our calculations. Uniform circular motion. This is a special case scenario when you're moving in a circle, but you're moving at a constant speed while moving in a circular path. So you're moving in a circle, but it's only at a constant speed. So when we're trying to find the average speed of something moving in a circle, we can take our familiar distance is equal to distance divided by time is equal to the speed. So when we're moving in a circular path, the distance is going to be the circumference. And the time it takes to do that distance is going to be the period, because the time for one complete cycle. And so circumference is equal to 2 pi r, and period is equal to capital T. So you have this equation. So this is equal to the speed something moving in a circular path. So again, this is a script versus a v. This would be velocity, and the script is speed. Okay. Oh, yep, had it right there. Okay. So in physics, you've got these two adjectives, rotational and angular. Depending on the textbook you're looking at, they'll either use these two interchangeably. I'm just going to use rotational because I think it's more descriptive. So rotational velocity. The variable for that is going to be a lowercase omega. Looks like kind of like a funky looking W. The equation for this is delta theta, which is change in angle over time. You describe this like how quickly you are spinning, rotating, or revolving. This is the rate at which you are changing your angle as you go through. That's where this equation comes from. So the units for that are going to, you got a lot of options. It could be degrees per second, could be rotations per second, it could be rotations per minute. This is known as RPM, rotations per minute. You might have heard of those, or radians per second. Radians, if you're in pre-cal, you recognize radians as another way to measure an angle. Equation for tangential speed. So this is just normal speed, and rotational speed that connects the two is the speed is equal to rotational speed times the radius. So radius is how far you are away from the axis of rotation. You must be in radians per second to be able to use this equation. Don't worry about making that transition. I'll just give you things in radians per second. The definition of acceleration. This is a review from when we first started talking about acceleration. This is the rate at which velocity changes. So we have acceleration is equal to change in velocity over change in time. So that was a review. But so if we're moving on to circular motion, if a car is going around a circular path on cruise control, it's moving at a constant speed, so it has a uniform circular motion. Is it experiencing acceleration? Correct answer is yes, because velocity is speed and direction. Though you're not changing your speed, you are changing your direction constantly as you go around a circle. So you're always changing your direction as you go in a circle. You're going this way, and now 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 you're going this way. It's always changing. Think of like changing north, east, south, west. That is always continually changing as you're moving in a circle. So we do have acceleration. We have a name for this, where you're not changing your speed, but you're simply changing your direction. Is known as centripetal acceleration. Okay. The equation for that centripetal acceleration is speed squared over the radius. Um, so this is different than speeding up going down. This is how quickly you're changing your direction towards the center of the circle. So it's not looking at your change in speed, but changing your direction. The unit for centripetal acceleration, check this out. So here you have meters per second, and we're squaring that. So, and then down below here, we've got meters. So this is meters per second, and then you're squaring that. When you square that, it becomes meters squared over second squared, and then over meters. And one of the meters cancels out with that one. You're left with meters per second squared. And if you remember, that is the norm. That's our unit for acceleration, meters per second squared. So regardless if it's centripetal acceleration or it's regular acceleration, it's still meters per second squared. The direction of this is always pointing towards the center of the circular path, just like the same direction as centripetal force. So centripetal force and centripetal acceleration are always pointing towards the center of the circular path. So what would cause centripetal acceleration to increase is if you had a greater speed, you're moving faster, or you have a smaller radius of curvature. You have a tighter circle, like that would be a small radius versus this would be a bigger radius. The smaller the radius, the faster you're changing your direction, the higher centripetal acceleration. Then to connect centripetal acceleration and rotational velocity, you have another equation that centripetal acceleration is equal to rotational speed squared multiplied by the radius. And finally, the equation for centripetal force. This is, remember Newton's second law, we have net force is equal to mass times acceleration. This is kind of a special case for moving in a uniform circular motion. We have centripetal force is equal to mass times centripetal acceleration. And if we incorporate what we know to be true for centripetal acceleration, that leads us with mass is equal to speed squared over the radius. That's your go-to equation for centripetal acceleration.